So good morning or good afternoon or good evening, wherever you are living. Today, we will be talking about introduction to analytic network process, or ANP for beginners, maybe we can say. Let me first introduce myself. I am a professor of decision sciences in Turkey, Industrial Engineering Department of Istanbul Technical University. And I have visited University of Pittsburgh 4 years ago. I finished my PhD in Istanbul Technical University and visited Leeds University Business School during my PhD studies. And not surprisingly, my research interests are decision analysis, multi-criteria decision-making, group decision-making, and operation research and management science. So let's start with analytic network process. As all you know, ANP is developed by Tom Saaty. It's an extension of AHP, we can say. And it's one of the most powerful methodologies we can use for combination and evaluation of decision makers' judgments. And by using this method, we can effectively either rank alternatives or choose one of them, a compromise solution, maybe classify them. It's not written here, so we can sort alternatives, or we can estimate some outcomes regarding to the problem on hand. ANP is a widely used technique. Why? Because we can use this method for structuring the problem, modeling purposes, and analysis of the problem when we have to make complex decisions. And it is based on mathematics. There is a huge theory behind ANP and also psychology. When we are talking about psychology, let me give you a brief example on cognitive psychology, and we will do an experiment together. We can say that people are not rich at aggregating large quantities of information on problems. When they face with cognitive overload, especially in complex problems, there are lots of elements, lots of factors to deal with, to analyze. They most of the time employ some heuristics. Maybe they use the decision for a similar problem they have made previously, or instead of dealing with the whole problem, they just deal with a small portion of the problem. And that leads to the selection of some suboptimal alternatives. Maybe there is a better alternative, but as they are using heuristics or they are using a small part of the problem, just dealing with that part of the problem, there can be some better alternatives. That's why we should have people deal with the whole aspects of the problem. And it's not so easy because of cognitive psychology. Now, if you are ready, let's make an experiment. Maybe you have seen this before somewhere else, but I hope you haven't. I will ask you how many factors can you consider at once. Actually, you will see the word remember on screen. And then I will have you try to recall the numbers in the order I have shown you, one after another. We will do this experiment first of all with 5 numbers, and then with 7 numbers, and then with 9 numbers. I hope 5 and 7 will go okay, but most of the time, especially my students, are failing for 9 numbers. So if you are ready, let's try. After seeing remember, one by one, you will see some numbers on the screen appearing one after another. So is there any volunteer to have a recall here for these 5 numbers? No one?
53724.
53724. Numbers are okay, but ordering is a little bit changing. 52734. Okay, let's do the same experiment this time with 7 numbers. Any volunteer? Okay, I can answer. 1, 8, 3, 6, 9, 1, and 7, I guess. Yeah, right. Actually, here my purpose is I will show you 9 numbers. Most probably you will fail. But if you try to group them 3 by 3, 3 digit, 3 digit, 3 digits, then it will be more easier for you. Let me show you 9 numbers now. So can you recall them one by one or three by three?
385, 162, 379.
Exactly, you are right. So as you see, when you consider them three by three, actually you are imitating your brain and you are not dealing with 9 elements, you are just dealing with 3 elements. Actually, this is one of the main roots of AHP, we can say. And here you are grouping and having some smaller parts of the problem and then bringing them together. Actually here, a participant has enabled closed captioning. What does it mean? I don't know, but let's continue. Actually, this is George Miller's famous paper, The Magical Number 7 plus or minus 2. We have some limits on our capacity for processing information. He published this paper in 1956, a very old one, in Psychological Review journal. And he indicated that the capacity of us, our short-term memory, is 7 separate items, plus or minus 2. I mean, the brain of a regular human can evaluate, can handle, tackle, process, differentiate, we can say different verbs you can use here, at most 7 factors. For some people, this limit can be decreased to 5. For some other people, it can be increased to 9. For some exceptional people, this can be less than 5 or more than 9. But normally it is 7, and that's why if you are using AHP model, analytic hierarchy process, in a level, you shouldn't have more than 9. You are not advised to use more than 9 elements. Or in analytic network process, in a cluster, you are not advised to use more than 9 elements. This 9 is coming from this 7 plus minus 2. So when people face with a complex problem, because of this psychological evidence I have shown you, in order to understand problem better, if you are not they are not using some heuristics or just dealing with a small part of the problem. To understand the problem better, they must break down the problem into some smaller parts, smaller constituent parts, and then they can construct a hierarchy or a network model to present it. And then after dealing with smaller parts of the problem, they aggregate everything together to find the whole process results. But there is a problem here, small, maybe big problem. In a hierarchy, we assume alternatives at the bottom level affects, influences, or depend on the criteria, and criteria affects goal. Sometimes we have sub-criteria. In this case, alternatives affect sub-criteria, sub-criteria affect criteria, and criteria affect goal. But we assume that in a hierarchy, criteria do not affect other alternatives at the bottom. Criteria do not depend other criteria, and alternatives do not depend other alternatives. But in real life, this can happen, especially for complex problems. These relations, especially, we can call them as dependence. And if this depends in both ways, both directions, it's called as feedback. We can have dependence and feedback. In this case, instead of hierarchies, we should use networks. Network models with dependencies and feedbacks actually improves the importance of criteria or preferences of alternatives. Maybe we can say priorities. We are revealing from judgments of decision makers, and our estimations are more accurate in this case for network models. But then you can ask why we are using hierarchy. Analytic hierarchy process is the most widely used method because it's very easy. And as you will see here, when you use analytic network process, actually you are asking a huge number of pairwise comparison questions, and decision maker can try to get rid of from you instead of answering all these questions. So if it is possible, you assume these relations do not exist. But if there are several relations, influences you cannot ignore, in this case, you should use network models. Here you see a very simple network model with 4 clusters. In each cluster, we have elements represented by dots, and there are some arrows. This is from Saaty's ANP book. Here you see, for instance, from C4 to C2, an arrow is going. This arrow is showing us the outer dependence. It indicates from cluster C4 to C2. its meaning is at least one of the elements in C2 here, at least one of the elements here, is affecting at least one of the elements in C4. By seeing this network model, actually we can understand which one affects which one. For this purpose, in the following slides, you will see, we are using influence matrices. At influence matrices, you will see row elements will affect column elements. But here we are just seeing which cluster is dependent on which cluster. This is outer dependence. There is another outer dependence from C4 to C3 and C1 to C2. If these outer dependencies are in two directions, as I have said, it is called as feedback. And if an element in a cluster is affecting another element in a cluster, at least one, in this case, we have inner dependence. And in networks, as I have said in the beginning, we have dependencies and feedbacks. Here you see a very simple example. There are two clusters. One cluster stands for purpose of usage of a dam, of a water reservoir. And second cluster represents in what level the water will be kept. And as elements, we have flood control, recreation purposes, hydroelectric power generation. And for water level, we have low level, intermediate level, high level. And both elements are affecting other clusters elements. So this is a feedback system, we can say. Here you see another example from Coke industry. In Turkey, once upon a time, I guess 20 years ago, something like that, Cola Turca launched a national cola brand, and we have famous Pepsi Cola and Coca-Cola. With a marketing professor, we tried to estimate their market shares by using ANP methods. And those who are familiar with marketing knows there are four important P's at marketing. One of them is product. Second one is placement. Instead of placement, we use distribution. The third one can be considered as promotion. Here we use this as advertisement. And the fourth one, missing one, is price. Their prices are near to each other. That's why we didn't use price as a cluster. But as you see, by using this Coke network, we predicted the market shares of these companies nearly to real values. Besides, when you make this justification, I will talk about Saaty compatibility index at the end, how we can make this justification, we'll talk about that. You are also having importance of the factors in each cluster. You see which one is more important, frequency or current impact or historical impact, by checking the limiting matrix values. We will talk about them. Here you see another example in Super Decisions screenshot. Super Decisions will be the software you can use. It's a freeware and shareware program, thanks to Creative Decision Foundation. They are doing a great job. And here you see an organic foods network with one of my PhD students we dealt with. Product groups, we have product characteristics, distribution channels, communication channels, projects, strategies, policies, consumers' buying motives. Here there is, we cannot see directly an alternatives cluster, but projects or strategies and policies can be regarded as alternatives cluster here. And sometimes we do not have any alternatives cluster in a network. In this case, we are just trying to prioritize, reveal the importance of criteria of the system. And you can use something as, for instance, a rating approach or another method to evaluate alternatives with the usage of importance of criteria coming from Analytic Network Process. So this is Super Decisions web page. Most probably you heard about this. And let me go back to theoretical framework of Analytic Network Process. As we say, there are dependencies and feedbacks. Together we can call them as interconnections. So ANP is a methodology that allows not only a single decision maker, but a group of decision makers, just like AHP does, to deal with these interconnections between the factors, between the elements of a complex structure of the problem we are dealing with to make a decision during our process. It's an MCDM method, of course. We can use them for complicated and unstructured problems, because during this process, we start with structuring the problem. We structure a network model. We model the problem by asking some pairwise comparison questions. And then we have analysis step. At analysis step, we find the priorities of the elements of the problem or the factors. So we use clusters of elements as I have shown you. And these would be the topics we will cover today. I hope we can do all of them. We will start with pairwise comparison questions. You are familiar with that. And also you are familiar, I guess, with Saaty's 1 to 9 fundamental scale. And then I will show you how we place these responses for pairwise comparison questions in a pairwise comparison matrix. And then we will calculate eigenvector. And also we will a little bit talk about inconsistency. Also, when we have more than one decision maker, there will be a group decision. There are two approaches there. I will talk about that. And then spatial matrices for ANP, I will try to introduce you. Supermatrix, it's also called as unweighted supermatrix, weighted supermatrix, and limiting supermatrix, which is shortly said limit matrix. And we will conclude with Saaty compatibility index. Actually, there are two more important concepts here I cannot cover because of time limits. One of them is benefit cost opportunity risk model. There are 4 subnets, benefit cost opportunity risk. Another one is sensitivity, but there is a special workshop for raw sensitivity. I guess you have done that previously. So let's start with pairwise comparison questions. Here at AHP, because of the one-way direction of relations, we are asking with respect to goal, which criteria is more important, that one or the other one? Or with respect to criterion, a specific criterion, which alternative you prefer, this one or the other one? But here, as we have a network, we do not have levels. Instead of levels, we have clusters. So each time, a sub-element can be a parent element at the next question. And therefore, after finding the influence matrix, I will show you in on an example, we ask of the sub-elements, which one affects, which one influences, which one impacts the parent element more, and how much more on 1 to 9 fundamental scale. Or of the dependent factors, we can ask which one influences the common factor more and how much more. Here you see the Saaty's 1 to 9 fundamental scale. It's both used in AHP and ANP. There are also other scales used widely, but this is the main scale we can use. If two elements have equal effect on the parent element, on 1 to 9 scale, of course, we are selecting 1. If the first element affects the parent element moderately more than the second one does, we are selecting 3. If this is strongly more, we select 5. If it is very strongly more, we select 9. If it is extremely more, we select 9. Of course, you can ask, there are also even numbers 2, 4, 6, 8. Of course, we can use them. But unfortunately, we do not have any verbal statement for them. These are the intermediate values. Here, there are 2 options, actually. One of them is if the decision maker you are posing these pairwise comparison questions is a clever guy like you and can understand what is going on, you can introduce this 1 to 9 scale. And then after asking these questions, you just get the answers as response. But if decision maker is not familiar with these issues, these subjects, in this case, you just ask verbal questions, get verbal answers. You yourself changes verbal statements to numerical statements, quantitative statements. Okay. And maybe you notice, I always said first element is affecting parent element more than the second one. Sometimes second element can be more effective on parent element than the first one does. In this case, we use reciprocal values, 1 over 2, 1 over 3, ... 1 over 9. So after getting all these answers, these paired comparison judgments of the elements with respect to the parent element are arranged in a matrix which is called as pairwise comparison matrix. Here you see a 6 times 6 matrix, again an example from Tom Saaty's book. We are trying to select a school for our kids or for some friends' kids. And we have learning friends, school life, vocational training, college preparation, and music classes. In this matrix, we have 6 times 6, 36 entries, but we will not ask 36 pairwise comparison questions for those who are not very unfamiliar with AHP, ANP, I am talking about this. Diagonal entries are filled as one automatically, because it's not, it doesn't make sense to ask which one is more important, which one affects school selection more, learning or learning. They are same, it's one. And we just fill this, I guess, pink or whatever the color is, this triangle, because when you ask which one affects more school selection decision, learning or friends, there is no need to ask again which one affects friends or learning by changing the places of the elements. If this is 3, this would be automatically 1/3. If this is 1/5, this would be automatically 5. That's why in the super decision software and in all other softwares, you will just see this triangle having n times n minus 1/2 questions. In this case, we have 6 elements, so there will be 15 questions here. N minus 1 comes from diagonal missing, and over 2 comes from this triangle will be filled, the other triangle, lower left triangle automatically. So in the software, you will not see the first column and you will not see the last row. Sometimes my students say, hey, this is wrong. We cannot see everything in our pairwise comparison matrix in super decision software. And I talk about this triangle phase. So we ask these questions. The order of questions can change. I am asking, first of all, learning friends and decision makers. For instance, let's assume that learning is moderately to strongly more important than friends. In this case, this would be 4. And then you can ask the second question, friends and school life comparison. Sometimes they compare learning with school life. They fill the first row and then second row. But I am using diagonal form. I asked this question. They said friends is very strongly more important than school life. And then this here says second element. So vocational training, second element means column. First element is row. Vocational training is strongly more important than school life. Here they are equal, here they are melody. One by one we get these answers. If, as I have said previously, if decision maker can understand what this scale stands for, he or she can just say you the numbers, or you get these verbal statements and convert them to numbers. You ask the other questions also, and then automatically as this first row is 4, 3, 1, 3, 4, this first column would be 1/4, 1/3, 1, 1/3, and 1/4. And now our pairwise comparison matrix is ready. What shall we do next? If you are not using any software, after filling all these matrices and preparing pairwise comparison matrix, you should convert this matrix to an eigenvector. And I will show you there are 5 different eigenvectors techniques most widely used. And based on these eigenvector values, we can say that according to answers of these decision makers, learning is the most important one. It has the highest priority. School life is the least important one. It's just 3.8%. And total, as you know, for an eigenvector is always 100% or just 1. So let's see how we can find eigenvector for paper and pencil solutions if you are making manual solutions not using any software. Here we have a small 3x3 matrix. We use column normalization. If you are not familiar with normalization, we are just talking about Manhattan distance-based normalization. For a column, for instance, here third column has 3, 4, 1. We get their summation, which is 8. We divide each value by 8, 3/8, 4/8, 1/8. In the first column, 1 over the summation, 2 over summation, 0.33 over this summation value. So after normalizing each column separately, we have a normalized pairwise comparison matrix. And then we get row averages of this matrix entries. It is the eigenvector. This is method 3. Okay. Now, let me show you other 4 methods, and then we compare them, and then we will skip this. At the first method, we first of all calculate row averages, and then normalize these average values. Actually, when you try to find average, you sum all values and then divide by the number of elements. So there is no need to calculate averages. Instead, you can calculate the sum of each row and then normalize the sums. Both of them give you the same results. For instance, this time the 4x4 matrix I have. And anytime if you have any question, you can ask me. I am going in a hurry because they said you just have 45 minutes, maybe 50 minutes. Here we get row sums. First row summation is 19, last row summation is 1.56. And then we sum these summations, find another summation, and we divide each value by the summation. We normalize summations. And this is the eigenvector with first method. If you get row averages, everything will be divided by 4. So this will be divided by 4. So eigenvector would be same. That's why there is no need to, although in the literature it says calculate row averages, we can just calculate the sums. It's the same. And second method says calculate the sum of each column, but do not normalize them. Just invert the summations and then normalize these inverse values. As you see here, we get summations and then we invert these values 1 over 1.51, 1 over 6.42, 1 over 11.3, 1 over 18. And then their sum is not 1, so we normalize them to get the eigenvector. The third method I already mentioned. For this 4 times 4 matrix, first we normalize each column and then we get row averages. And I advise you to use this method for paper and pencil solutions or manual solutions because the first two methods are a little bit far away from the real values you can find mathematically. The fifth method is the best method. And let me show you the fourth and fifth methods in this case. At fourth method, we calculate geometric mean. If you haven't heard about geometric mean, actually, it is a multiplicative form. Arithmetic mean is an additive form. As we are using ratio scale for 1 to 9 fundamental scale, multiplicative form, getting an average in a multiplicative form is better. For instance, in the first row, we multiply 1 by 5, and then by 6, and then by 7. As there are 4 elements, we get the fourth root. It is 3.8068. We do this operation for other rows also. After calculating all these geometric averages, we normalize them. This is the fourth method. And of course, finding the fourth root when you are making paper pencil solutions is not so easy. That's why I advise you to use the third method. And the last method the software uses is raising the pairwise comparison matrix to a larger power and then utilizing method 1. And then raising that large power matrix to a more large power matrix, again utilizing method 1, and comparing two eigenvectors you are finding. If they are converging, they are nearly the same, you stop. If not, you go to larger powers. That is how method 5 works. So let's see this in an example. The square of our pairwise comparison matrix is something like this. And then we get, we use the first method, take the summations, normalize them. This is the first vector for second power. For fourth power, we do the same operation. As you see, this is 6247, but this is 6180. They are not very near to each other. And we go to sixth power. At the sixth power, we have these eigenvector, red values are eigenvector values. At the eighth power, as you see, if we use just 4 digits after decimal point, they are exactly the same. And at the rest of the vectors, there is a small difference at 10,000 digits at the second and the fourth one. And they compensate each other, of course, because both of them should have a total of 1. So we can stop. So let me show you all eigenvectors we revealed from 5 different methods. As you see, this is the most accurate one mathematically. And the first and second methods, unfortunately, are very far away from real values. But the third method also is not so near, it's not so converging. But among these three, the best values is coming from the third method. So if you are using some paper pencil solutions, making manual solutions, you can use the third method. But when you use third method, especially I'm telling this to my students, and if you solve the problem with software, you will not find exactly the same solution. The reason is at method 5, they are using method 1 several times for large powers of matrices. So I guess we can continue. Okay. Let's a little bit talk about inconsistency. This is a very famous issue. Most of the time you are asked what are your matrices consistent or not. Actually, we are using this inconsistency because This is a descriptive approach, first of all, not a normative approach. As you know, AHP, ANP are descriptive approaches. They are not normative approaches. They do not say you should use this rule. So decision maker can be a little bit inconsistent, but sometimes decision maker can misunderstand you during the question phase, or you can misunderstand the decision maker, or especially in student projects, when they ask to foreigners, let's say, they try to get rid of the questions and they just make up some answers, random answers can come. To see whether these problems arise or not, we can calculate inconsistency. As I'm returning back to small example, 3 times 3 example, pairwise comparison matrix, we have calculated eigenvector. If pairwise comparison matrix is A, capital A, and eigenvector is W, we multiply this matrix with this vector. 3 times 3 matrix multiplied by 3 times 1 vector gives us another 3 times 1 vector, which is this one. And then these two vectors entries are compared. We get ratios. First element over first element, second element over second element, and third element over third element. As here n equals 3, n is the size of the matrix, our ratios would be around 3, a little bit more than 3 or a little bit less than 3. And then we will get the average of these ratios. It is called as lambda max, maximum eigenvalue. And then we will use this lambda max in an equation like this, lambda max minus n over n minus 1. Here n is 3, and lambda max is 3.0183. This is called as consistency index. For our problem, consistency index is 0.92% or 0.0092. And also in the books you can see in the literature, the matrices filled with random numbers several times, and they have calculated consistency indices, and the average values are given. For a 3 times 3 matrix, random index is 0.52. And you divide consistency index by this random consistency index of the appropriate size, and it is 1.76%. This is how the software calculates consistency ratio. If it is 0%, everything is consistent, but this is not our ultimate goal. Our ultimate goal is actually having decision maker be happy with these eigenvector results. But if this is more than 10%, sometimes you can say 11, 12, 13% are okay. But if this score consistency ratio is very high, 25%, then there is a problem here. If you have opportunity to asking again, you should ask again to decision makers some of the pairwise comparison matrices. If you have no chance, and if, for instance, you have conducted a questionnaire survey, a pairwise comparison questionnaire survey, in this case, you can discard, eliminate these answers having high consistency ratios or inconsistency ratios, let's say. And you do not see 2 here because when you have 2 elements, actually you are asking just one question. So there is no chance of having consistency. Just one answer will come. And our last topic from before skipping to special matrices is group decision. In group decision, a group may be working together, maybe in the same room, and they can discuss each judgment, each pairwise comparison response to arrive at a consensus judgment and have a facilitator enter it into the model, into the software they are using. Of course, here they should convince each other. If there are some people can say first element is more effective, some people can say just opposite. They should discuss and convince each other. But sometimes they cannot convince each other. Or sometimes it's not possible to collect all group of experts together in the same room in the same time. In this case, we ask their individual opinions one by one. For instance, conduct a survey. If this is the case, or if they cannot convince each other, although they are together in a room, you can use geometric mean to aggregate their results. Now, a little bit talk about this geometric mean issue in group decisions. For instance, for the school example, mother can say learning is strongly more important than friends, and father can say friends is strongly more important than learning. In this case, in Turkey, most of the time, what mother says happen. Learning is strongly more important than friends is selected. But of course, in an objective way, one decision maker is saying first element is strongly more. The other one is saying just opposite. Their average should be equal. Let me show their matrices. One of them picked 5, other one picked 1/5. Okay. So here, if you try to aggregate their judgments and have an aggregated pairwise comparison matrix, for X, we should have average of 5 and 1/5. If you use arithmetic mean here to combine these decisions, aggregate these decisions, 5 plus 0.2/2 is 2.6. But as I said, it should be equal. You should have 1. But average is 2.6, so it is wrong. Besides, if this is X, this should be 1/X. We talked about this. This is the reciprocal matrix. And here we have another 5 and 1/5. Its arithmetic average is same, 2.6. This 2.6 is not 1/2.6. That's why I say no to arithmetic mean. If you use geometric mean on the other hand, 5 times 0.2 or 5 times 1/5 makes 1. Square root of 1 is 1. And similarly, 0.2 times 5 square root is also 1. So geometric mean is better. This is just very simple example why we use geometric mean instead of arithmetic mean. Of course, theoretically, as I have said previously, this is a multiplicative average, and ratio scale is a multiplicative form, not additive form. So let's skip to our famous matrices, the supermatrix. The supermatrix actually is a matrix where you have all the elements in the network. If you have 5 clusters with 20 elements, you will have a 20 times 20 matrix. Each element will be represented at the rows and at the respective columns. And the eigenvectors of the sub-elements with respect to parent element after getting the responses of decision makers will be placed at the column of the parent element and at the rows of the sub-elements. Okay? And then you will see whether this matrix is a column stochastic matrix or not. Column stochastic means column totals are 1 or not. Just like Markov decision process, there we have row totals S1 because probabilities totals are 1. Here we should have a column stochastic matrix. But if you place for a parent node more than one eigenvector, in this case, total will be more than 1. It can be 2, 3, 4. What shall we do? We will convert our supermatrix to a weighted supermatrix if column sums are not 1. In this case, there are 2 options again. You can have all clusters equally important. In this case, you just normalize, because if total is 4 and if all clusters are equally important, you divide each value by 4. Or if clusters are not equally important, in this case, you should ask some pairwise comparison questions for clusters effect on clusters. And eigenvectors will show you these priorities, the importance of clusters. You will use this importance of clusters to come up with weighted supermatrix. In an example, I will show you this. After finding weighted supermatrix, which is a column stochastic one, you will raise this supermatrix, weighted supermatrix, to a significantly large power to have converged or stable values. Here, the meaning of this is, in the first row, you will always see the same number. In the second row, you will see another number, and always you will see in each column the same number. That is convergence. Sometimes convergence or stable values will not exist. You can see some zeros, or you can see 2 different patterns repeating themselves. If the matrix is not a reducible or reversible matrix, theoretically, I'll not go into detail. In this case, limit matrix will fail. So in the beginning, maybe you should try to find the limit matrix, whether it converges or not. If it doesn't converge, do not ask pairwise comparison questions to decision maker. There are 2 things here you can do. One of them is finding some new relations. For structuring the problem, I forgot to mention, we ask some questions, first of all, which factor affects which factor? And let's assume you ask this question to 10 different experts. And you say as a threshold, if at least 7 of them says there is a relation, you assume there is a relation. Instead of 7, you can decrease this threshold to 5. After this change, there'll be some new relations in the aggregated influence matrix. And when number of relations increase, maybe your matrix can have a limit matrix at the end of the process. But if there is just a few number of relations, or after changing this, you cannot find any relations, in this case, you will assume these a few number of relations do not exist, and you will return back to hierarchy. Instead of using network, if there is just a few number of relations, you assume they do not exist, and you can come back to hierarchy. There will be a goal, cluster names would be criteria, elements would be the alternatives or sub-criteria, and you will continue in this fashion. Now let's return back. The values of this limit matrix are the priorities we want to have. They can be importance of criteria, preferences for alternatives with respect to goal at the system. So let's see all this stuff in an example. Let's assume there are 2 clusters. In the first cluster, we have 3 elements. At the second cluster, we have 2 elements. And these are the relations. Of course, they are not readily apparent here. You should ask the decision maker by filling this influence matrix. After asking these questions, let's assume some elements will affect some elements here. And to denote that, you can use X, you can use star, you can use plus. It's up to you. I used X values here. The meaning here is A1 affects A2, but A1 doesn't affect A3. A1 affects B1 and B2. As I said, if you have a certain number of experts, you can have a threshold value. If they say, let's say 6 of them says, okay, A1 affects A2, among 9, let's say, you say, okay, A1 affects A2, but just one of them says A1 affects A3, others says, no, there is no effect, you are leaving that entry empty. After finding this influence matrix, now we are ready to go with Analytic Network Process second step, modeling. What shall we do? We will find which parent element is affected by which sub-elements. A1 is being affected by A2, A3 at cluster A, B1, B2 at cluster B. Here you should be careful. We will compare which one affects the parent A1 more and how much more, but we will do this comparison within the same cluster. I mean, we will compare A2 with A3, and then we will compare B1 with B2, but we will not compare A2 with B1 or A3 with B2. They are in different clusters. We'll make our comparisons in the same cluster. So we will have a pairwise comparison matrix for A1, A1 parent node, A2, A3 sub-elements of cluster A, and another pairwise comparison matrix again for parent element A1, this time from cluster B, B1 and B2. And answers are coming as 4 and 3. And you should also be careful, another important issue. A1 affects A2, but A3 doesn't affect A2. So there will be no pairwise comparison matrix. But if you are doing paper, pencil, manual solutions, you shouldn't forget this. You should write here one, I will show you. What else I have? For A3, I will compare B1 and B2 effects. For B1, I will compare all A's, all of them are affecting 3 times 3 matrix. For B2, I will compare A1 and A2. And then one by one, I will calculate eigenvectors. And good news, if you are using Super Decisions or a similar software, all this math will be done by the software. You will place all these eigenvectors to the supermatrix. How? For instance, this 0.8, 0.2 belongs to A2, A3 sub-elements when A1 is parent element. And A1 column, A2, A3 row will have 0.8 and 0.2. Okay? And as A1 just affects A2, there is no other A elements affecting A2. Here you should write down 1. I forgot to mention, if there is no relation, it's automatically 0. If you forget this, this would be also 0. And you will making some miscalculation. Because of this relation, you should have just 1 here. Actually, as you know, total of the eigenvector values is 1. So there is no eigenvector here, but just 1 element. That's why we use 1 here. All other eigenvectors are placed. So this is our unweighted supermatrix. As you see, column totals for the first column is 2, second one is 2. So just one is enough for us. This is not a weighted supermatrix. You should not immediately start taking larger powers of this matrix. First of all, you should find weighted supermatrix. At this weighted supermatrix, if clusters are equally important, you will make normalization column by column. First column summation is 2. So you will divide each value by 2. 0.8 over 2, 0.2 over 2 will come here. Second column, 1 and 1 I have, total is 2. Again, each value is divided by 2. But at the third column, total is 1. So it would be same. You will not divide it by 2. Because at the end, for weighted supermatrix, all columns total should be 1. If you make some miscalculations, it can be 0.5, 0.3. Don't do that. And then fourth column, total is 1. So it's same. But last column, total is 2. You divide each value by 2. This is the weighted supermatrix. Now we are ready to get higher powers. And limit matrix is something like this. As you see at the first row, I am always seeing the same numbers, 3103. At the second row, 1950, 1950. Okay, this is limit supermatrix. Then clusters are equally important. If you want, you can have cluster normalizations. The 3 numbers total is calculated. Each number is divided by summation. And you have 100% total for the cluster elements. And also for the second one, you make this normalization. Actually, ranking will not change. Here, A1 is the highest valued element. Here also, A1 is the highest valued element. But if you are talking about some percentages, it would be better to get these normalized values. At the software, both of them are given. Limit values and normalized values in 2 columns are given to you. If clusters are not equally important, I guess I should finish. In this case, first of all, as you see, A and B cluster elements are affecting A cluster elements, and also A and B cluster elements are affecting B cluster elements. You should have cluster comparisons like this. After getting answers, you will calculate eigenvectors, and you will use these values instead of dividing by 2, dividing by 3, or whatever it is. For instance, here, 0.8, 0.2 will be multiplied by 0.8. 0.75, 0.25 will be multiplied by 0.2. 0.8, 0.2 are coming from AB cluster comparison with respect to A cluster. Similarly, here are the results. 1 will be 0.8, this one would be 0.2. But here, total is 1, so nothing would change. It's same. Also at the fourth column, everything is same. But here, the total is 2. So we will not use 0.8, 0.2 this time. We are at B cluster column. We will use 0.75 and 0.25. We will multiply these 2 values by 0.75 and 1 by 0.25. And this would be our weighted supermatrix. This is done when clusters are not equally important. Most of the time, I assume clusters are equally important because we are asking lots of questions. So cluster comparison questions will increase number of questions, but especially if clusters are not even distributed, you can ask these questions. And limiting matrix is a little bit changing. Again, you can have normalization here. So I am skipping this DAM example. You can see this example in the book. This is the first network I have shown you, feedback network. Here you see some inner dependencies because you can assume water level is an alternative cluster, or dam water reservoir usage is an alternative cluster. Alternatives are, let me show you the vector. Alternatives are connected to each other. Fluid control, fluid control, recreation. And these eigenvectors are coming from the pairwise comparison matrices I skipped. At the end, this is a supermatrix. We assume 2 clusters are equally important. So we make normalization here. And then we get the highest power, 64th power gives us this converged matrix. This is the limit small supermatrix. And then you can normalize them and advise the managers of this dam not to use this dam for flood control, for other purposes, and keep the water in high level. And last issue is Saaty compatibility index. It shows us how close our estimations revealed from ANP model, the cluster values, to actual data, for instance, market shares. There are lots of different examples in the ANP book you can see. If this is vector of actual data, A1, A2, A3, and if this is the vector of estimations coming from the cluster of network model, you convert this time vector to pairwise comparison matrix. How? A1 over A1, A1 over A2, A1 over A3, and so on. Here you do the same operation, but this time you use transpose of this fashion here. B1 over B1, B1 over B2, B1 over B3 comes to the column, not row. And then you use Hadamard multiplication. Most probably, if you're not familiar with ANP, this is the first time you are hearing about Hadamard multiplication. At least I was some people like that. Hadamard multiplication means multiplying entries in the same position. First row, first column is multiplied by first row, first column of the other matrix. And you have 9 entries again. You get the average value of these entries. It is Saaty compatible index. If this is exactly 1, these two vectors are exactly same. Then there is no need to do anything. But to see how much your estimation vector is near to actual vector, you can use the Saaty compatible index. If the value is near to 1, then you are justifying your network. And there is an important remark here. Most of the time, especially for market shares, there are some big players, big companies, but also there are some other players. In the industry, if other players' total percentage is 20%, you should get rid of this 20%. You shouldn't compare these 3 values with these 3 values. You can, it would mislead you. You should first of all normalize this because total is not 1 year. Total is 80% because of this 20. After normalization, now total is 1 or 100%. You should compare these two. So that's it. Thank you for listening to me. In Turkish, teşekkür ederim. In all other languages. If you have any questions.
Wait, that was too fast. I cannot say it in Turkish now. You have to teach us.
I can teach you anytime. Is Greek somewhere here? I cannot see. It should be somewhere here. Eferisto, you say, right?
Yeah, you're right. Good.
So you can ask me any questions now, or here you can see how you can contact me in any means. You can get in contact with me. Thank you for listening to me, and thank you to organization committee for giving me this opportunity for organizing this workshop. If you have any questions, I can get.
Thank you. That was amazing in 45 minutes.
Yeah, I try to do my best. Actually, Rozan said you couldn't do this in 45 minutes, and she was right. I was just in a hurry. Okay, then. Thank you. Maybe we can see you at the next.
There might be some questions.
Okay.
There might be, not
silence,
from me, but
I guess
somebody might ask.
Okay, please. There is silence. No question. In this case, maybe you can ask me a question.
Is being too clear, huh?
Okay. There are 2 options here. I am very clear, or I couldn't tell you anything.
Actually, it was amazing.
Thank you. Okay.
It was really amazing.
Thank you very much.
Thank you.
Thank you.
See you at the next one. Bye.
Bye-bye.
Have a nice one.